Now we're going to be talking about nucleophilic addition reactions. These are the reactions that aldehydes and ketones undergo. For that, we're going to learn a couple of mechanisms under acidic condition and under basic condition. And then we're going to understand how that works with different nucleophiles. So the main mechanism that you're going to be seeing is, again, we have one under basic condition, and we're going to have another mechanism under acidic conditions. So what is that? Let's just have an example of ketone. Let's draw acetone for the basic. And say that we're making it react with hydroxide. So under basic conditions, the mechanism is, again, we're talking about nucleophilic addition. Why does a nucleophile, an electron-rich species, and here the carbon at the carbonyl is electrophilic. So you're going to have a nucleophilic attack, what we call direct attack on that. So under basic conditions, you will have that. And of course, because you open that up over to the oxygen, this is going to be an O negative, and you're going to have an OH here. All right. And so at that point, what we do say, if you are under basic conditions and you have water is your acid and your conjugate base is OH, say that you have that in the reaction vessel. What's going to happen after is the protonation, and this is a hydrate. Okay. Other reactions that happen with through that mechanism under basic conditions is the Grignard reactions, for example. Say that I have this and I'm using now ethyl magnesium bromide in dry ether, diethyl ether. So here, remember that this bond is polarized. It's almost like an ion pair, and you will have, we're going to divide that nucleophile that way. And so that is a very strong nucleophile and a strong base. So that's why it needs to be under dry conditions. You will have the direct attack. And here, let's do O negative. And here you will have at the ethyl group. So I'm going to add 2 carbons. That's the ethyl and the methyl. And in a second step, so say step 1 and step 2, we protonate. Let's say that you have added acid or even water to that, and you will protonate. And in that case, because you added this too, you're going to form a tertiary alcohol. A reaction that you probably have seen before, how to synthesize alcohol. So here we're using Grignard. So those are examples of the mechanism under basic conditions. So this is important to know. What species do you have when you are protonating? Notice that here we are, that's one step, and after this is done, you add the acid or the water to protonate. Here you can have that in the same flask. You have water and OH, so you do the hydrate. So I'm going to erase one of those to work on the mechanism under acidic condition, and I'm going to use the same example of the hydrate. Typically, aldehydes are better. The equilibrium is more shifted to products for aldehydes in the case of the hydrate. So let's do that under acidic conditions. So what do you have? What species do you have under acidic condition? Well, you will have, say, hydronium, the major species that you have, and you will have water as your conjugate base. So we need to keep that in mind. So now I'm going to draw the reaction. Now the mechanism under acidic condition is a little different. In this case, in the basic, we did nucleophilic attack first, and then we had a proton transfer. Oh, here I'm going to draw water like explicitly here, showing that this is a proton transfer step. The second step is proton transfer. And what happens under acidic conditions? Under acidic conditions, we don't have OH. We don't have a strong nucleophile such as here. So the first step is actually a proton transfer. This time we have hydronium. Is your acid? Again, we are working under acidic conditions. So always in that case, the first step will be a proton transfer, and you're going to be protonating the oxygen of the carbonyl compound. When you form this, now you're making the carbon more electrophilic. Remember that we can do resonance here. And if we do, that would explain why after protonation, that carbon is more electrophilic. The resonance structure places a positive at the carbonyl. And so your hybrid will have delta positive more, be more positive than it was in the ketone that is not protonated. So the first step is then proton transfer, not a nucleophilic attack. But since you have now this species that's more electrophilic, a weaker nucleophile will work and better. And that weaker nucleophile is water. We don't have H. So we're going to add water and do the nucleophilic attack over to that protonated species. I am going to do another color here because I'm running out of ink. Okay, now, when you do that nucleophilic attack, and my arrow starts here at the lone pair, the species that you're forming here is, I'm going to have OH after moving that over there, of course. Here, let's do the other method. In here, you're attacking with water. So now you have an intermediate that is formal positive. So the second step is nucleophilic attack. And we need a third step under acidic condition. And that third step is another proton transfer. So let's draw water. Notice that because we are in acidic conditions, we don't have OH. The base is going to be water. So you're going to get that extra proton, and you're forming the hydrate again. I'm going to draw it in a different way. It's the same thing, right? So we have two OHs in the product. So here, notice again the difference. In the acidic condition mechanism, you do proton transfer first, making the carbon more electrophilic. Then you do a nucleophilic attack. This nucleophile is weaker than OH, of course, but since the carbon is more electrophilic, that goes well. And you have an extra proton in this intermediate product, and you need another proton transfer step. We're going to be using all of those analogies now, studying different nucleophiles when we do nucleophilic additions over carbonyl compounds.